So that means I told you many times, if it is temperature value, you should put it in Kelvin. If it is difference in temperature, it's okay to calculate directly from the Celsius because of this principle. This 273 and this 273 will cancel. So that's why, even if I write a Celsius or Kelvin, doesn't matter. Okay, so these two will cancel. So the kg cancels, Kelvin and Celsius will cancel. So do this math, and that will give you the Q1. And that will be in joules. Multiplication, division, it's not my department, it is your department. Similarly, Q2. Okay, I don't have space here. So since it is straight line, I told you it's not MC delta T, it is M into L F. M is 3 kg. LF is latent heat of fusion of ice. Latent heat of fusion of ice is given as 3.35 into 10 power 5 joule per kg. 3.35 to 10 power 5 joule per kg. So the kg cancels, so I'll be getting joule. So again, multiplication your department. So do the same thing for Q3. So MC delta T. M is again 3 kg. C is specific capacity of water 4186. Delta T is you are taking from 0 degree water to 100 degree water, which means the delta T is 100. So do the math and find out the joule. Similarly, do the Q4. Q4 is for steaming. Latent heat of vaporization. Latent heat of steam is 2.256 into 10 power 6. Joule per kg. This is in kg. So kg cancels, so I'll be getting joules. So simply add Q1, Q2, Q3, Q4, you'll get the answer. So the total energy required will be Q1 plus Q2 plus Q3 plus Q4. Very simple, absolutely nothing difficult if you understood the theory. If you have not understood the theory, then it's going to be difficult. So that's why I want you to focus more on the theory first. Then you can do the numericals. Take it down quickly. I will keep this screen for a while. So if you are copying, quickly copy it. 20 seconds. Okay, anybody still copying? Can I share the screen? Okay. Okay, we talked about the fifth question, example. I don't think we did any problems in heat transfer. So, conductivity. Can anyone check your notes? Did we do this one? 1.6. What is the temperature of the steel copper junction in the steady state system? For the steel rod. Anybody? I think I did talk about this in theory. So why nobody is answering? I'm asking a simple question: did we do this problem or not? You just check your notes and tell me 1.6.
Sir, also I wasn't happy. We did not do this 11.6.
1.6. Okay.
We did not do it.
Will not do it. Okay. I remember talking about this in the theory. Okay. Let's see. Since you folks might find it difficult, that's why I'm just thinking that I need to do more problems on this. PDF is being very slow. 11.8, I did it. I remember doing that. Okay. So let's do one problem with the thermal conductivity. And then, yes. Again, I'll give you the method. Okay. You have to do the multiplication division also. What is the temperature of the steel copper junction in the steady state of the system shown in figure 11.5? 4.5. So it's so steel copper junction is over here. So what is the temperature of this junction temperature? So this is what is asked. Length of the steel rod is given, length of the copper rod is given, temperature of the furnace is given, temperature of the other end is 0° icebox. Area of cross section of steel rod is twice that of the copper rod. That means 2 times this area is here. Thermal conductivity of steel is given, of copper is given. So as I told you in the theory, right? The heat flow rate will be same. This is something like a series connection. So since it is something like a series connection, the heat flow rate will be same, but the voltage difference or the temperature difference can be different. Okay. So that means I can say that the heat flow rate in the H1 should be equal to H steel, should be equal to the heat flow rate in the copper. That should be equal to the overall heat flow. Something like I is equal to I1 is equal to I2. Heat flow rate means I told you thermal conductivity K area by L delta T. Delta T is Tj minus 300. Sorry, 300 minus T. What is Tj? Junction temperature. Thermal conductivity. So this is for steel. This is for steel. This is for steel. Here you have thermal conductivity of copper, area of copper, length of copper. Then the difference in temperature will be Tj minus 0. So thermal conductivity of steel is given. Thermal conductivity of copper is given. Area of steel is 2 times the area of copper, which means I can write this as 2 times area of copper, which means the area of copper will get cancelled out. 7 because I'll be getting 2 here. Length of steel and length of copper rods are given. So substitute all these numbers and calculate the Tj. So that will be your department. Since 300, I am putting it in Celsius. This will also be in Celsius. If I put this in Kelvin, then this will also be in Kelvin. So since it is series connection, the underlying principle is current is same. But what is current in thermal physics? It's nothing but the heat flow rate. What is voltage in thermal physics? Anybody? What is voltage in thermal physics? In reality, there is no such thing as voltage in thermal physics. But what is the analogy? That is the equivalent. Equivalent. Okay, now is talking to you. We should quickly. Iron bar L1 length is given, area is given, K1 is given, and the brass bar L2 is given, area 2, K2 is given. Are soldered end to end as shown in figure. The three ends of the iron bar and the brass are maintained at 373 and 273 Kelvin, respectively. Obtain expressions for and hence compute temperature of the junction of the two bars. So I need to find the junction. Equivalent thermal conductivity of the compound bar. And the heat current through the compound bar. I think I would say it's very similar to what we did. Okay. So you can try this yourself. If you're not able to get it, I'll help you. Okay. So basically, the compound bar. Suppose if you say that you had a steel and brass bar like this. If you are making one single bar, what will be the thermal conductivity for that? This is steel and this is brass. So what will be one single object and what will be the thermal conductivity for that? So in that case, you would substitute. You can equate this information to one more thing. Sorry, iron and brass. Okay. It's not steel, it is iron and brass. So iron and brass, suppose if I want to find the equivalent thermal conductivity, what I can do is the equivalent thermal conductivity, I can write it as with this. The area should be the same as these two things, divided by length will be 2 times the total length here. Area 1 is 0.02, area 2 is also 0.02, which means the compound bar will also be having same thing. So area 1 and area 2. Into the temperature difference. So temperature difference means it's between this part and this part. So which means it will be 373 minus 273. So it will be 373 minus 273. Again, I'm not talking about this example, I'm talking about the next example I will first say. So K equivalent is what is asked. Area is known, length of iron and length of brass is known. This can be equated to this side. So K for iron is known. area of iron is known, length of iron is known. Temperature, you must have found it from the previous calculation. You must have found the Tj, which means 373 minus Tj. So if I have calculated Tj from the first part of the question, then I could have, I can substitute over here, and then I can calculate the K. I don't know why in the textbook it looks so complicated. This should be supposed to be easy. Okay, try this. Okay, if you are not able to get the answer, maybe I can help you. Okay, let's see. Okay, so I think we'll go to the exercise problems. Triple point means it's a point where ice, sorry, solid phase, liquid phase, and gaseous phase, all the three can coexist. That is what is called triple point. Something like a melting point and boiling point. So melting point means where ice and water coexist. Boiling point means where water and steam coexist. Similarly, there is something called triple point where all the three states can coexist. Sir, how is that possible, right? How can you even get, when it is ice and water, how can you get steam? The answer for that is, right now we are doing the experiments, all these discussions which we had is based on constant pressure. But suppose if I change the pressure, right? If I change the pressure and if I make pressure as one of the axes, then there will be a triple point. So that discussion is given over here in the boxed items. So I don't remember which page it is. Yeah. So you have to go back and read this triple point, right? So try to understand what this means. But as I said, when you bring in the atmospheric, all these discussions which we did was in atmospheric pressure. But suppose if I start changing the pressure, then you will get some situations like this. Okay. So for example, this line is the location where as the temperature and pressure are changing, here it is liquid and here it is vapor. So in this line it is liquid and vapor. Similarly in this line, right, this is your melting curve, which means solid to liquid. And this will be your solid to vapor, so which means it will be sublimation. Liquid to vapor, this will be boiling. Okay, so this is given for A was for water, this is for carbon dioxide. So don't get confused, what is triple point. So triple point is a situation where all the three states can coexist and the pressure is different. Okay. For example, in our case, in water case, you know that whatever we are talking about is in atmospheric pressure. Atmospheric pressure is something like 1 atmosphere. So 1 atmosphere is somewhere um, somewhere here. But if you reduce the pressure to 0.006, then you will come to a point where solid, liquid, vapor, all of them can coexist. Okay, so maybe this is not required for your exam purpose, but learning something new is always in interest. So go through it. If you have any doubts, you can come back and discuss that. Okay, let me check my book if I given some easy, difficult, medium markings. Okay, luckily I have marked some easy, medium, and difficult. Let's take it down. One point one. So the easy ones are 1.1, 2, 10, that's all. So easy ones are only these things. The medium ones are 1.3, 5, 7, 8, 9, 12, 13, 16, 17, 19, 'difficult ones. Let's see, 11.6, 0.11, 14, 18. Okay, so mark it down. As you do some problems, you will at least know that which are the problems you can actually try yourself. First, you have to try all of them. But at least the easy and medium you can try it. Okay, not the difficulties. Okay, let's do some simple, easy ones first. Triple points of neon and carbon dioxide are 24.57 Kelvin and 216.55 Kelvin respectively. Express these temperatures on the Celsius and Fahrenheit scales. You know that degrees Celsius plus 273 will give me Kelvin. So if I subtract, same, right? So using this formula, I'll be able to calculate the Celsius. Once I calculate the Celsius, I think we studied as formula for Celsius and Fahrenheit. So F minus 32. Was that anybody remember? Can you check your notes? 5 by 9, 9 by 5. Celsius. Anyone check this? Thirty 32 Fahrenheit will be equal to Celsius. Celsius is a percent. Yes. So now we asked to check your notes. Point 8, yeah. So Celsius, 1 by 5 is that, means that US is actually plus 30. Using these two formulas, we should be able to calculate. And 1.3, I think, is medium, so let's try that. Electrical resistance in ohms of a certain thermometer varies with temperature according to the approximate law R is equal to R01 plus alpha T minus T naught. So as the temperature changes, the resistance of the thing changes. So the resistance is 101.6 ohm at triple point of water, which is 273.16 Kelvin, and 165.5 ohm at normal melting point of lead, 600.5 Kelvin. What is the temperature when the resistance is 123.4? So this resistance is 101 and this resistance is 165.5. So 123 is falling somewhere between this and this. So the Kelvin temperature should also fall between this and this. So that's the first thing, recognizing. So the value should fall within these two values. Okay, let's try this. T naught, what should I take it as? Okay, let me try writing it like this. So resistance here is 101.6 or not, I do not know. So 1 plus alpha T minus T naught. So the temperature here is given as 273.16 minus T naught. If you write for the second case, I'll be getting 165.5 ohms is equal to R naught 1 plus alpha. This temperature is given as 600.5 minus T naught. So in this particular case, what will happen is I will be getting 1, 2, 3. So it will be like 3 unknowns. But I have only 2 equations. So in that kind of situation, what I can do is I can take one of this given data as a resistance for R naught and T naught. So this will be taken as a reference point. So that means, again, as I said, they should have mentioned which one is the reference. But since they are not given which one is the reference, I'm going to assume that the water thing is the reference. So R is equal to R naught 1 plus alpha T minus T naught. So if I take this as the resistance 165.5, R naught, I am going to take this as the reference. So 101.6. 1 plus alpha, I do not know. Alpha is a constant. So T minus T naught. What is the temperature? 600.5. Minus what is T naught? That's the reference temperature. So 273.16. So now using this, I'll be able to calculate the alpha. Once I calculate the alpha, I can substitute it again in the same equation. So again, take it down. I'm not going to do the multiplication division. It's your duty to do it. So what is the temperature when the resistance is 123.4, which means they are given the resistance 123.4. R naught, again, I can take it as the reference point, which is the water stream. Not 1.6 resistance for water. Sorry, not for water, but this triple point of water. Alpha, now that you found the alpha, I can substitute over here. So alpha is known. T is the temperature which they are asking. T naught is 273.16. First standard, you will have these kind of problems. Okay, so we'll study more about this later. But in some cases, you will have to do this like this. We'll be dividing this by this, so these two will cancel out. Okay. Still, I don't know how to calculate. I will not be knowing the alpha and T naught. Okay, for now, take down this. This will be the method. Anybody still copying? Can I change the screen? Kapil?
Yes.
Okay, very good. So Ashwant is still alive. Let's see others. I don't think others are alive. Okay, let's continue. Anybody else still alive? Nobody?
Sir.
Siddharth is alive, okay.
Yes, sir.
Kevin is alive.
Yes, sir.
Smart. Anybody else? That's all. All the others are not alive. Okay. Okay, let's see which other problems which you can do. 11.5, something to do with the yes. Okay, let's try the fifth one. Two ideal gas thermometers, A and B, use oxygen and hydrogen respectively. The following observations are made. Pressure thermometer A, pressure thermometer B. Okay. What do you mean by pressure thermometer? As the temperature increases, the pressure will also increase. So that means if I'm able to measure the pressure, I can also tell the temperature, okay, by having some kind of a relationship. And which we studied as Boyle's law or Boyle's law, Gay-Lussac's pressure law. Okay. That's what we mean by pressure thermometer. The previous problem we talked about something called resistance thermometer. Okay. What do you mean by that? As temperature changes, the resistance of a wire will change. And from that, if I'm able to measure the resistance, I can tell what is the corresponding temperature. Here is the same thing. Instead of resistance, we are measuring pressure. So triple point of water temperature, pressure thermometer A is showing this much value. Pressure thermometer B is showing this much value. Normal melting point of sulfur is having a pressure of this much, pressure of this much, and pressure B. A and B use oxygen and hydrogen respectively. So this is oxygen, this is hydrogen respectively. What is the absolute temperature of normal melting point of sulfur as read by thermometers A and B? So I need to find the temperature of melting for sulfur using this information. Triple point of water, I think I'm going to take this as a constant, which is 273.16. So just now I showed you that there is something called triple point. Just like boiling point, melting point, there is something called triple point where all the three will coexist. Okay. So that value happens to be 273.16. So minus 273 means it will be 0.16 Celsius. Okay. So what is the absolute temperature of normal melting point of sulfur as read by thermometer C? Okay, so if I try to find the relationship between this and this, I know that Gay-Lussac's pressure law. Gay-Lussac's pressure law says that pressure is proportional to temperature. Whenever we have proportionality, we'll bring in a constant. This can also be written as P1 by T1 is equal to P2 by T2. Okay, so if you compare two different situations, this will be true. So if I'm considering this as P1 and this will be P2. So this is P1, this is P2. This is T1, this is T2. So this is known. So take it down properly. I'm not going to do it. So P1 is given, P2 is given. For 10 power 5, you can cancel it out. T1 is given, they are asking to find the T2. That's all. Okay. So my job is to read through the question and tell you that, okay, this is the principle you have to apply because we are talking about Yale-Lusak's pressure law. And you should understand that temperature can be measured with different methods. If you measure the resistance and tell the corresponding temperature, it's called resistance thermometer. If you measure the pressure and tell the temperature corresponding temperature, then it's called pressure thermometer. If you measure the voltage and then tell the temperature, then it's called thermocouple. So there are so many different types of measuring temperature. Anything else that comes to your mind? Anybody? You can also have volume thermometer, right? So as the temperature increases, the volume of the gas increases, which means if I measure the volume, then I can easily tell the temperature. But they asked you to calculate for thermometers A and B separately. So that means in first case, this will be the case. In the second case, this will be taken as P1, this will be taken as P2. This will be taken as P1, this will be taken as P2. So you have to find out two things. Do it for A and B separately. What do you think is the reason behind the slight difference in answers of thermometers A and B? So obviously you should expect the same answers, right? So the normal melting point of sulfur has to be the same. So the T2 value should be same. But looks like maybe you will get a small difference. Thermometers are not faulty. What further procedure is needed in the experiment to reduce this discrepancy between the two readings? So this requires a little more discussion. Okay. So we'll talk about this in the kinetic theory of gases. So there is something called the ideal gas situation. So the ideal gas assumption. So take it down for now, but when you study the kinetic theory of gases, this will make more sense. Ideal gas assumption is true only at low pressure and high temperatures. So low pressure and high temperatures is where one molecule and another molecule, right? If it is low pressure, then it's kind of farther away. If it is high pressure, right? Molecules will be very close to each other. So this is low pressure and high temperature. This low temperature and high pressure, then the molecules will be close. Close to each other. Whereas here molecules are farther away. So because of this reason, we will say that there is not much of a intermolecular forces of attraction here. So take it down properly. This is coming again in the next chapter, kinetic theory of gases. I mean the later chapter. So this will happen. Low pressure and high temperature will lead to molecules being farther away. So no intermolecular forces of attraction. And the molecules will be close to each other, means it will be high pressure. As you keep on increasing the pressure, you are putting more and more molecules closer to each other. So that means high pressure means it will be like this. High pressure and low temperature. In this case, there will be intermolecular forces of attraction. So because of this reason, what will happen is the ideal gas assumption will be affected here. So the ideal gas only in this situation will be close to ideal gas behavior. This will be like a real gas, which means that be some intermolecular force of attraction. When that happens, this ideal gas equations may not be working accurately, which means since these oxygen and hydrogen are not ideal gas, they are real gases. There will be definitely some differences. Okay, so only if you understood all these things, the final sentence will make sense. So take it down. Oxygen and hydrogen behave as real gas, not as ideal gas. So the values will be off. Off from the real value. Okay, so in a way we are doing only approximate calculations. Okay. So you know something about pressure thermometer. Okay, you know which format to use. They use as pressure law. So this is additional information. So I hope you have copied it. 1.6 given as difficult. 1.7. Let's try the medium ones first. A large steel wheel is to be fitted onto a shaft of the same material at 27 degrees Celsius. The outer diameter of the shaft is, so shaft means it will be like a cylinder. Okay, so that will be your 8.7 diameter. So the wheel is going to look something like this. So this hole, this has to get in. Diameter of the central hole is, the wheel is 8.69. The shaft is cooled using dry ice. So you know that if I heat it up, it will expand, which means this size will get bigger, which means it's even more difficult to get into this hole. Okay, or putting this wheel inside this shaft. But suppose if I put dry ice, so that is something like now very, very cold. So the temperature will decrease. When the temperature decreases, it will condense. Sorry, it will contract. So when it is contracting, right, the size will get smaller. When the size gets smaller, it's easy for me to put it. So very in the workshops, very often they use this kind of methods. Okay, they will use some dry ice, or sometimes they will use a built-in torch to heat it up. Okay, so instead of cooling down, I can heat up this. When it is heated up, this will expand slightly, and then it's easy for me to insert it inside here. Okay, so make a note: welding torch or dry ice. So dry ice to cool it down, welding torch to heat it up. Only if you understand the engineering or physics behind it, you will understand now what the problem is trying to say. Otherwise, you'll be wondering, sir, why are we even using dry ice here, right? So you see, this is not a problem related to specific capacity. This is a problem related to dimension changes. Okay. So the expansion concepts. What temperature of the shaft does the wheel slip on the shaft? So at some point, right, this will be equal to this 8.69. So that's what I'm supposed to find. Assume coefficient of linear expansion of the steel to be constant over the required temperature range. So we studied something called delta L by L is equal to some constant alpha into delta T. Remember this, the very beginning we studied this. So this alpha is your linear thermal expansion coefficient. Alpha L linear, yeah. You are right. I should write alpha L. Since it is linear, I should write plus L. That's the area, I should write as alpha L. So alpha L is given. Delta T initially it is at 27 degrees Celsius. So I need to reduce it to some temperature which they are asking you. At what temperature? I mean, this can be written as T minus 27 degree. If this is put in Celsius, this will also be in Celsius. This was in Kelvin, this will also be in Kelvin. What is the delta L? This is 0.7, this is 0.69, which means it will be 0.01. So this has to be reduced by this much. Original length is 8.7. Is equal to alpha L. So this is known, this is, you know the numbers, which means you can find this. That's all. Very simple. Any questions, any doubts, anybody? No doubts? Okay. Okay, let's see. 2.9. That's where. All these things, even though I said medium, it's direct formula only. You can try that. .12 is an interesting question. Let's try that. These are all, we are already done a lot of examples. So try these questions for yourself. Okay. If you bring any doubts, I will be happy to help you. Okay. But if you don't even try it, I don't know what to say. Okay. You can come to the center also in the weekends. Come here and work out the problems, clarify your doubts. You can also do that. You have all the options. A 10 kilowatt drilling machine is used to drill a bore in a small aluminum block, mass 8 kg. So it means we have a aluminum block. It's aluminum and it's 8 kg block. We have a drilling machine, so it's a 10 kilowatt drilling machine. So let's say this is a drill. The drilling machines will look something like this. Usually it will look vertical, but it have some horizontal machines also. So when you go to machine shops, you will see a lot of CNC machines, computer numerically controlled machines. So sometimes you will see something called DMCs, and sometimes you will see something called HMCs. So H stands for horizontal machining center, V stands for vertical machining center. If you go into some machine shops, you'll be able to see these things. So when you come across these words, that's what it means. All these things are CNC machines. Meaning if you enter the program, if you enter, okay, you have to, what we will do is, as a manufacturing engineer, we will take the drill and we will put it over here. And the drill, based on the diameter of the drill, you know where the machine is standing. And from there, we'll say, okay, go 5 centimeter in the x-axis. And then do the drill. So drill it up to say 20 centimeters, something like that. Okay, so all these things are programmed inside the CNC. So once we program it, once we do one single block properly, and once we study properly and then program it, what will happen is, for every aluminum block, you don't have to manually keep on doing this. So you put it inside the machine, and then the machine itself will be doing this. Okay, so that's where all CNC programming becomes very, very important. So that's how all these automotive parts are made. If you keep on doing each and every part separately, it will take a lot of time. So what we do is, the first thing, first time we have to do it, and that's what is called proving engineers. As proving engineers, we have to prove that the entire program is working correctly. Once it is done, then you just put the program and it will keep on running perfectly. Okay, maybe those things are not required. It's only for additional information in case if you have interest in manufacturing engineering. How the computer programming comes into picture in manufacturing. Even inside your car, right, there's some microprocessors, meaning it's like a computer. So the computer is actually controlling, how much fuel is injected in the different cases. Okay. So depending upon what you are doing, whether you are accelerating or braking, those kind of situations, the diesel injection or petrol injection will be changed. And that's again a computer controlled fuel injection. Why I'm saying all these things, even though it looks like separate engineering fields, computers are used in automobiles, electronics, electrical engineering is used in automobiles. So everything will be coming together. Okay, 10 kilowatt drilling machine. So this is 10 kilowatt. Okay, I think I got sidetracked. I was talking too much here. I didn't see the time. So 8 kg. How much is the rise in the temperature of the block in 2.5 minutes? Assuming 50% of power is used up in heating the machine itself or lost to the surroundings. Specific aluminum is this much. So let me quickly give you the method. Okay, you can try it as usual. So 11 point. So 50% of the power is used up in heating the machine itself or lost to the surroundings, which means only 50% is. So if I say 10 kilowatt power, not the entire 10 kilowatt is applied inside this block. Only 5 kilowatt will be applied over here. Okay. Which means I can say heat lost is equal to heat gain. Because they're asking you what is the rise in temperature of the aluminum block. So 5 kilowatt power will be going into this machine because 50% power. And when I say heat loss, we're talking about energy, heat energy. In 2.5 minutes. So that means power is, you know that power is equal to work by time. So if I want work or energy, I should multiply power and time. So how much energy is given from here, right? So 10 kilowatt, kilowatt means 10 power 3. I told you it is only 50% efficient. The remaining is lost here, which means only this much will be going inside. And time is 2.5 minutes to 60. Because I'm converting into 60 seconds. So this will be joule per second, right? Power is nothing but joule per second. This will be in seconds. So seconds will cancel. Efficiency does not have any units. So I will say seconds and seconds will cancel. So I'll be getting in joules. So similarly, on the other side, heat gain will be MC delta T. What is mass of the aluminum block? 8 kg. What is specific capacity of aluminum block? It's given as 0.91 joule per gram per Kelvin. 0.91 joule per gram per Kelvin. You see, this is in kilogram, this is in gram, so I cannot cancel this. That means I have to multiply by 10 power 3 to convert it to grams. Only then I can cancel this. You see, that's why I keep on saying that you have to write the units also. By that way, you will not make any mistakes. Delta T is what they're asking. So they're asking you what is the temperature rise. So the room temperature is it given? Oh, they're asking you to find the rise in temperature, which means they're asking you to find the delta T. Okay, so do this math and you'll find the delta T. That's all. So you see, if I write the equations after this, it's very, very easy. But how do I arrive at this? You know, they are given an engineering problem. So only if you understand all this background, you will be able to attempt this problem. So that's why I'm just talking all these things. Okay, so I'm going to stop here. So next class, I'm going to get started with oscillations. Okay, so if you try some problems and if you come back and ask me doubts, I'll be helping you. Okay, if you don't do it, then no, I can't do much because we're running out of time. So we have to go further. So it is your duty to try out at least 4 or 5 problems other than what I have done. So if you come here and ask me doubts, I'll be able to help you. Okay, thank you all. Bye.
Thank you, sir.
Thank you, sir.